Good morning everyone, my name is Gokul Adethya and I'm going to teach about deep learning and how to perform gradient descent. In deep learning we use neural networks, which is nothing but just stacking multiple linear layers with non-linear activation functions in between. Our goal is to find a particular function that approximates the given distribution from the observation and try to predict what happens when we go beyond the observation. So let's say we have this particular sinusoidal curve with some additional Gaussian noise added to it. This is our observed training data set. We try to fit a particular polynomial over here, our function approximator, so that we are more curious about what happens beyond this particular point. What is going to happen? What is the output for the unobserved future values? So for a sine curve over here, the ideal answer obviously would be a Taylor series. And interesting thing about Taylor series is that when you try to expand the Taylor series for a more higher number of higher order, the Taylor series approximation is much more closer to the sine curve. This is actually very synonymous to the observation in neural networks. So when you have multiple linear layers stacked against each other, it becomes more dense, you could say. And if you have more sort of activation, linear layer, activation function, linear layer, activation function basically introduces the non-linearity. The neural network is able to approximate much more complex polynomial. It is able to fit similar to the Taylor series. So more complex and more denser the neural network is, easier to approximate and fit the complex neural networks, complex polynomials. So let's say we take this particular set of equation as our neural network. So basically a linear layer, a ReLU for activation function, and another linear layer. So it's just a composite function in a manner. So ReLU function is nothing but a nonlinear activation function, which basically looks something like this. It basically leaves the positive values as it is and sets the sets the negative values as 0. So over here the weights and bias, which are the W1, W2, B1 and B2, the variables that we call it as parameters, something we need to optimize. So for a given function approximator that we have right now, given the observed x value in the current observed distribution, we have these particular parameters, and we are able to calculate some particular output y from this particular function approximator. And our goal is to make sure that this particular y is as close as to the y hat, which is the actual ground truth to the observed value. So our goal is to find the ideal set of parameters that can satisfy this particular constraint. And over here we apply this constraint using the MSE loss. So MSE is nothing but mean squared error. So it basically decreases the distance between the y, the predicted, and the y hat ground truth. And this we call as loss function or the objective function, which is the goal and the constraint. And how do we attain it is using the gradient descent algorithm. So it's nothing but finding the slope. So let's say this is the particular loss curve. The curve is between the loss function and some particular weight, say W1. And let's say for an assumption this is how the landscape would have looked like. We ideally wouldn't be able to see this is the landscape because in a neural network usually you have millions of parameter, and it will be like million factorial combinations to find the landscape. So for now, let's say we take a 2D space over here. So this is the initial set of parameter, and we apply gradient descent. So what we do is that find the slope over here, which is basically this particular direction, and we try to move against the slope. And we do it iteratively till that we achieve a local minimum. And let's say we if the algorithm says to overshoot over here, and we attain this particular parameter point in the landscape, and the slope again will invert to this particular direction, and if we go to the opposite direction we again achieve a local minimum. And there's something really nice about this algorithm because at some point you sort of converge to the local minimum. But again, I'm saying that as local minimum because let's say in this example, this is the entire landscape. If we explore in a much more wider research, and this is the initial position of loss curve. And if you apply the gradient descent, we would get stuck up over here. This is the local minima ideally. But then what we would have needed for a better fit is an even lower score, which is the global minimum over here. So this is an issue with gradient descent algorithm. It's widely, it depends on how you initialize the values and how you optimize the gradient propagation. So if we are instead been over here instead, the weights initialized over here, we could have attained the global minimum. So yeah, so the derivatives, the slope is found using the derivatives, taking the derivatives at this particular point with respect to that particular parameter, which we call it as gradient, and we subtract the gradient from the parameter itself. And how do we calculate it? So that's by actually saving the intermediate step during the forward pass, which is nothing but just computing the composite function, the linear layer, the relaxation function, and the next layer, and the loss function. After calculating this particular loss function, we go on moving forward towards finding the partial derivatives. So we calculate the dou L by dou y by dou W2, and so on with respect to other values. Now, ideally, we need the partial derivative of W1, dou L with respect to W1 other parameters, the dou L by dou theta. And for all these parameters, we just apply the chain rule. So, if you apply chain rule, we will get dou L by dou y by dou A1, dou A1 by dou Z1, and dou Z1 by dou W1. And we just have to plug in these partial derivatives we just computed during the forward pass, and then we'll end up with a really nice equation over here. And this can be applied for every other parameters. So let's try to take up an example and see how it pans out in the real experimentation. So this is the sin-x curve with some Gaussian as I mentioned before. Let's say we take an architecture, instead of 10 neurons in the first layer. So instead of taking W1, a scalar, we take a vector, and that's the entire difference. And we just have to aggregate and sum it up. Let's say we initialize just once for all the biases and 0.5 for all the weights. This is something I'll come back to later. This is the ReLU activation function and the corresponding derivative. And this is how the gradient looks like. So this is sort of the graph. It sort of implies what happened in the forward pass over here, and what happened, how we are calculating the gradient accumulation and going backwards and able to find the gradient for each particular parameter. So we also do a equivalent Pytorch implementation, and when we run it, we actually end up with a much better score in Pytorch implementation compared to the Numpy implementation. And you can see the Numpy graph actually shows a really bad curve. The curve is not even non-linear, to be honest, just an x-axis. So where did we go wrong? That's because Pytorch, instead of using the name weight installation, use a much more intelligent weight installation called Kaiman installation. It tries to sample the weights and biases from Gaussian distribution. And why do we do it? You can see after training the weights, the resultant optimal weights with respect to Numpy and Pytorch model. The yellow are the Pytorch model and the blue are the Numpy model. All the weights in the particular layer 1 are the same values, whereas all the weights in bias 1 are same values. And similarly for the second layer 2. This happens only in Numpy but not in Pytorch. Why does it happen? So if we try to see it over here, let's say this particular W1 we discussed before is meant for a vector with 10 neurons as we saw in the program, and if we see the gradient update for it over here, which we calculated before, it is not proportional to the weight itself. In fact, it's more it's sort of constant for all the vectors, all these individual weights in this particular vector. So W1, W2 until W10, everything will have this exact same gradient update through the entire iteration for the Numpy model. So because of that, what happens is that when we if we initialize with W1 for all the weights, all the 10 neurons weights, we, even after getting some ideal W after multiple iteration, we just end up with an equivalent of 10 into Wx1, which actually could have been just sort of equivalently written as W dash x1 with a single neuron. So what we did just now is that instead of having 40 parameters that we can tweak, basically a 40 dimensional space, we just degenerated into a 4-dimensional space, because it could have been just as well represented using a single neuron. So because of that, we just limited our exploration space right now. and this is what caused the underfitting curve we saw in the Numpy model. So if we go back to the implementation, let's see what happens if we try to have the same initialization for the Pytorch model also. And yeah, we can see the same degenerative effect as we saw in the Numpy model. So I'll just revert it back. Okay, so let's see how the landscape looks like. So this is the landscape for the Pytorch model, and you can see the Pytorch model achieved a 0.15 loss, whereas the Numpy model achieved a 0.522. And this landscape, you can see the Pytorch model achieved a sort of a local minima over here, and similarly you can see it from above. So even the Pytorch achieved a 0.517 in local minima. It's just local minima because the global minima we tried to explore gave a 0.14, which is much more lower. So what we can see is that the gradient descent algorithm is able to give a good approximate local minima, but not a global minima. And in fact, if we try to explore this space even further in a larger scale, we could even find a much better global minima. And if you try to see in the Numpy scale, due to bad initialization over here, it got stuck in a saddle point over here. So what happened is that all the surrounding values you can see over here, the z values are the exact same. It's because of this, the slope around this region is also zero, because all the surrounding values are also zero. And because of this, it will never truly be able to move or get away from this particular position, because all the gradient values will also be zero. And this occurs of different weight initializations, and we have to try to use something much more intelligent, something such as Kaiman weight initialization, where they try to sample it from the Gaussian distribution. Yeah. Goodbye.